So in this video, I wanna discuss why convergence is important. Why convergence? No, why convergence is important. And why do we have different kinds of convergence? So you will see you have pointwise convergence, but that is only one kind of convergence, not necessarily the best. It's not really the best. Okay. So let me start with an example. So example. So we know that we have x. Let's say we have x between 0 and L. Okay. So we're gonna find the Fourier series of x between 0 and L. This is L, right? And so when we find the Fourier series of x between 0 and L, it turns to be this one: x equal 2 times sum n equals 1 to infinity L over n pi minus 1 n to the n plus 1 sine n pi x over L for x between 0 and L. Okay, L. But now we know we can do, just for review this, we can make this is a sine series, so it has to be symmetric with respect to the origin, so the extension will be like this, minus L, and then will be periodically going like that, right? And so on, right? So that's just to discuss how the extension, right? So that's how this series is gonna look around periodically. Okay, so the extension, periodic extension, is gonna look like that. Okay. So so I don't know if you guys remember, the person that is gonna talk about Taylor's theorem is gonna say that let's say you have in power series, inside the radius of convergence, you have f of x equals sum n equals to, let's say, 0 to infinity of x minus a to the n over n factorial. Okay, so turns out that inside the radius of convergence you can find f prime of x, and f prime of x is gonna be the sum n equals 0 to infinity the derivative of this guy, so there will be n times x minus a to the n minus 1 over n factorial. So basically this n cancels with this n and you'll get n minus 1 factorial. Okay, so and I'm not being warning, not very specific. Warning, I'm not providing specifics. Okay. But you know, under certain conditions inside of the radius of convergence, if you have a function that is expressed as a power series, the derivative will be just you interchange the derivative with the sum, and you just have to find the derivative of this guy inside the sum. So let's see what happens here. So let's assume we can interchange derivative of x with the derivative with the infinite sum, derivative with the sum. So what does it mean? I'm gonna take derivative with respect to x, both sides. So this is derivative with respect to x, and then 2 times the derivative of this guy, the derivative of the whole thing, and then finally I'm just gonna assume, and I don't know if this is true, but let's say that we think it's true. So 2 times sum n equals 1 to infinity derivative with respect to x of the inside guy. So the inside guy is all this. So let's write it down. L n pi minus 1 n plus 1 sine n pi x over L. Okay, so what is that derivative? This derivative is 2 times sum n equals 1 to infinity, and this derivative is, these are constants, L, n pi, all these guys are constants, so they stay the same. Times derivative of sine is cosine n pi x over L times n pi times the derivative of the inside, so times n pi over L. So this n pi cancels with this n pi, L cancels with L. So finally I just got this guy. What is the derivative of x? The derivative of x is 1. So my question is this the cosine, is this the cosine Fourier series expression for f of x equals 1? So the answer is no. Okay, so if you calculate it, go ahead and calculate the cosine Fourier series of number 1. It's gonna be just 1. So turns out that you cannot just interchange the sum with the derivative. Okay, so it's important, and here in Fourier series we don't have radius of convergence. Have you noticed that in Taylor's theorem you have radius of convergence? Okay, so that's what I wanted to some people to make presentations on Bessel functions, Legend, all those, because for those functions you need to find the radius of convergence. It's not big deal, it's easy. But then you can find the derivative of the inside and everything. You can integrate those functions. It's very extraordinary. But in Fourier series we have this problem. But don't worry, we have some good, nice theorems. I'm gonna list the theorems just for completion. You know, like I need to give you a warning. Like, you are a mathematician, you are not an engineer. You need to know that these series are not perfect. They don't converge. You can just not find derivatives as you want to. So that's the way it goes. So let me give you some theorems here to justify when you can find the derivatives, and then I'm gonna give you a really nice application of this, and you're gonna be able to use it when at the end of the class. Is gonna help me to introduce the new calculus. It's called distribution theory. It's called weak derivatives. And this is mathematics from 1960. So this is recent mathematics, okay? Because all this mathematics is old. This Fourier series is also old, okay? Not as old as calculus, but still is old. So some theorems of convergence. Theorem: a Fourier series that is continuous can be differentiated term by term if f prime x is piecewise smooth. Okay, so the derivative of the function has to be piecewise smooth. Okay, but and uh, this is kind of incomplete. Uh, and there is a second version of this theorem because it looks like we don't have enough information. So there is this version. So I like this version better. If f of x is piecewise smooth, then the Fourier series of a continuous function f of x can be differentiated time by term, can be differentiated. So let's put part 1, part 2, can be differentiated term by term if f of minus L equals f of L. So this is for full Fourier series, okay? So let me give you a nice application. So let's consider again f of x equals x. So we're gonna do f of x equals x between 0 and L. And then let's do so if you do the cosine series for this one, cosine series is gonna be x equal L over 2 minus 4 L pi squared sum, and these have to be the odd ones, n is odd only, it's 1 over n squared cosine n pi x over L and x between 0 and L. But we know that when you grab this series, is not give you doesn't give you only it doesn't give you only the doesn't give you only this approximation to this line. Is gonna give you the whole thing to minus L and L, and then it's gonna extend it periodically, and so on. Okay, so let's keep, and then okay. Okay, so here this extension, notice that minus f of minus L and L is the same. You see, well, this one's supposed to be this one, right? So they are the same. So and f prime of x, well, at least this case, we can use number 2. If f of x is piecewise smooth, so this piecewise smooth is soft here, it's soft here, it's soft here, it's soft here. Maybe it's not different. Smooth means differentiable, okay? Maybe it's not differentiable here, maybe it's not differentiable here, but it's differentiable here and this. So it has a countable number of not differentiable points, and that's not a problem for us, okay? Or I mean, for this new calculus, for classical calculus, yes, this is a big problem. So it turns out that I can find the derivative of this guy. even though I have those corner points, yes, that's what is the amazing thing. This theory is already giving you an idea that there are new concepts of derivatives. So if I find the derivative of this guy, it will be the derivative of x is 1, the derivative of L2 is 0, the derivative of this is constant, so it's minus 4L pi squared. Now I change the derivative. I'm not gonna, the derivative of this guy, I'm just gonna interchange, I'm gonna put it inside, so I'm gonna put the derivative inside the sum. So I'm gonna get the sum 1 over n squared and the derivative of the whole thing, right? But the derivative of 1n squared is constant, so it's just a constant. So the derivative of cosine is minus sine n pi x over L times n pi over L. And this is n odd. Okay, so this minus times minus give me plus, and then yeah, I mean this n cancel with one L, and then I get pi over L. Okay, is that right? Yeah. Okay, so this one okay, I have some also another simplifications. See, this L cancel with this L, this pi squared cancel with this pi. So finally I get 1 4 over pi sum of n odd 1 over n sine n pi x over L. Okay, and this is the Fourier series. This is the Fourier series, the Fourier sine series of 1. But look at the amazing thing, okay, guys? So at this point, I mean, you should be proud of yourselves for choosing to take this class. What do you think is the derivative of these guys? So this is x. So what is the derivative of this line? Is 1, right? This is minus x. What is the derivative of this guy? It's minus 1, right? So it's go minus 1 and 1, right? So somehow I'm gonna have derivative between 0 and L is 1, and the derivative between minus L and 0 is minus 1, and then what happens at the corner, at the point? Well, that's a point, that's a corner, so it's undefined, so I should have something like that, right? And the same repeats everywhere, right? So I should have in between, this is L, this is 2L. So between L and 2L, what is going to be my derivative? Minus 1. And then between 2L and 3L, it's going to be 1. And then undefined. And that's those points. And keep going, keep going, keep going. Okay, so that's my intuition talking to me. Now let's forget about that. Now let's graph this. This is the Fourier series of 1. So I know how to graph that totally independently. So between 0 and L, I had 1. But this is, now I'm gonna, I had to graph the extension. What is the extension? This is a sine Fourier series, so a Fourier sine series, so this is odd. So I had to do the symmetric. The symmetric is minus 1, right? The symmetric is minus 1. But we have whole and whole, right? And this is minus L. Okay? But then we know that it is, because it's Fourier sine series, this is my odd extension, so it's going to extend periodically. So it goes like like this, run, run, and so on, run extended periodically. So turns out that is giving me a new concept of derivatives. So I can find the derivative even on the corners when I have those corners. So it's giving me a new concept of differentiation. Okay, so I think that's very cool. So so uh, so I think you can appreciate how this new theory is giving you insights for what is next on calculus. Okay, and yeah, so this is one of my last this is one of our last videos on Fourier series. Okay, so we are moving on now to solve partial differential equations.